Hey guys, what's up? Eddie Alho here with KissAnalog.com. Alright, so today's video is about negative resistance. It's a very important concept in the switch mode power supply. It's one of those concepts that's kind of easy to grasp. You go, oh yeah, I got that. But then there's a lot of permutations. There's a lot of, not permutations, but there's just a lot of things that go along with it. You know, a lot of effects it has, or ramifications it has within the circuit design and or even testing power supplies. So it's kind of good just to focus just on negative resistance, see what it is, and just talk about it for a minute. So that's what we're going to do. I'm going to demonstrate it with this boost converter that I have here. By the way, I'll put a link below. I think I've reviewed this one. I think this was one I used in a review, but I explained how the boost converters work. I'll put that link below. And this HP power supply, this Harrison power supply, is going to be our input power supply to our, what I'm going to call this power supply, and this the boost converter. And the red lead comes in, goes through this Habo test, which I'll put a link below. I've reviewed this guy, nice meter, and it comes out into the input of the boost converter. And the negative lead just comes straight through right into the boost converter. So that's the input side, and this guy, this Fluke 27, he's going to monitor the voltage there at the input. And by the way, I just did a review on this one. Super cool. Look inside this one, and that's I'm going to give this away on Father's Day to Patreon. You can become a patron for as little as $1, by the way. So I gotta support my patrons, right? I only got a small handful right now, so yeah, I gotta do something for him. I'm gonna give this guy away. And then this amp probe, which I just reviewed, again, link below. This is a really nice, super well built meter. I think every bit as good as any Fluke. I've got a bunch of Flukes here. I've always been a Fluke guy, but since I've been doing this channel, I've been buying other meters and really impressed with the amp probe. You got to see the insides of this guy. And the case just feels great. Anyway, sorry. But we're going to use this to monitor the voltage here at the output, right here at the Conduction load. So the lead length, the current going through, we're only going to set this guy for 1 amp, so it's not going to lose a lot of voltage, but any voltage lost, we'll detect it here. And this is an adjustable boost, so I'm going to adjust this for 30 volts here, okay? So right about 30 volts. So when I plug this in, you'll see some current here, you'll see 20 volts here, you know, pretty close to 20 volts, and then pretty close to 30 volts here. Let me just show you this board here. I made some notes. It's a basic concept, negative resistance, and we're going to talk about what it is and why it's important and how Ohm's law is affected, or how you use Ohm's law to look at it. And this is for switch mode power supplies. Alright? So just wanted to show that board here, and now, by magic, I'm going to show you the board again with something else on it. Alright, back in the flash. So I've got a little circuit here, the HP power supply, the boost converter, and the Conduction load. Okay? And then what I've shown is our red and black leads. It's the current in. I showed it as a loop because whatever current goes in comes out, right? So we got VN and IN. And this is my little eyeball looking in for resistance, okay? What's the resistance looking into this? Well, if we have voltage and we have current, we can find out the resistance. Well, our output, we're going to set at 30 volts, and the current's going to be set for 1 amp. There's my I. So looking into this, the impedance that this boost converter sees is RO is equal to V out over I out is equal to 30 ohms. 30 volts over 1 amp is 30 ohms. Oh wow, look, that just came out of nowhere. So this is our little Ohm's law formula, right? Little wheel. So if we want to find resistance, we cover it up V over I. It's V over I. I just want to put that up there for those that want to see where the formulas come from. You just cover up the letter you want, and if you cover up the V, it's I times R, and cover up the I, V over R. So in this case, R, so we cover that up, it's V over I. Alright, so for this first example, we're going to put 20 volts in, we're going to find out what our current is, and then we're going to calculate our R. Okay. Alright, and I've got it all set up, so all I have to do is push this in, and voila. And this is kind of a cool meter, this Havo test. The display goes amber when the current's an amp or above, kind of showing dangerous current, I guess. Okay, and there we go, about, just, there we go, 20 volts in, and just slightly over 30 volts out, so just slightly over 30 watts, 1 amp. Cool. Okay, let's write that down and calculate it. 1.66, well, we'll say 1.67 amps, okay? Okay, did the little math, 1.67 amps, we need to find R, right? So it's V over I, and that comes out to 11.98 ohms. Cool. This guy is 30 ohms, and now we found out this boost converter is 11.98 ohms. Nice. So this is a constant current, so it's going to have a constant voltage, so it's going to look like constant resistance. And if I were to take a resistor like this that is 4 ohms, 200 watts, it's 4 ohms. Or if I was to put this in place of the boost converter on this power supply, I could raise and lower the voltage and calculate I and get this R, right? So if I were to do that for this next situation where we put 10 volts at the input, then I could use R since we know what it is, and I could find out where I is. Because this is always great when you have two knowns and you want to find out an unknown, right? But we're going to find out that that's not going to work. Maybe you guys already know. Probably do. But I'm just trying to, you know, present the situation and talk about it. But okay, let's just do it. Let's just drop it and see. So as on a, you know, on a resistive load, if this was a resistor here, and as we lower the voltage in half, the current should drop in half. Okay, so let's just do it. And we're at 20 volts. I'll drop down to 10. You can hear the HP kind of buzzing because it's putting out a little more current now. Okay, that's right at 10 volts. And look at that, our current went up instead of down. Our voltage went down, but our current went up. Kind of did the opposite of what a resistor would do. So that is in essence what negative resistance is. Okay, it's doing the opposite of what you would think a resistor should do. Okay, 3.5 amps, let's calculate that. And meanwhile, alright, so here we go. With the 10 volts we had 3.5 amps, which calculates out to 2.85 ohms. Wow, that dropped quite a bit. And that's really the kind of the point here. You know, this changed, doubled from that. This dropped in half. And that's kind of interesting. You know, that kind of makes sense, because if you look at the power formula, if we consider power at the input, the power didn't really change. 20 times this current is equal to half that voltage times half or twice that current, right? That looks pretty much equal. The trick is the output power stays the same. It's always 30 watts. It's always 30 volts, 1 amp. As long as this boost converter is doing its job, it's going to maintain a certain power output. So power supplies, it's not a voltage supply or a current supply, it's a power supply. So I mean, in the true essence, it's providing power, and constant power, because the load's constant current, the voltage is being regulated by this constant, so this is all constant here. The only thing that can change is over here. So we need to maintain constant power, meaning these three things. So you cover up P, it's I times V, so it's I times, you know, I times V. So those two things have to maintain the same, you know, relationship. If this drops in half, this has to go up twice to compensate. Going back to the resistance, this power supply, when it's looking into this converter, it was seeing 12 ohms, and then it dropped down to less than 3 ohms. That's what that is. It's about a power of 4, because both the voltage dropped by double and the current went up 2. So these things both changed 2 times. So this had to be, 2 times 2 is 4. So this had to change 4 times. That's what we call negative resistance. Okay, now why is that important? Well, if your power supply is designed to operate from, say, 10 to 20 volts, then the resistance that it's looking into, your power supply is looking into this guy, at sometimes you might say it's 30 watts out here. Well, if somebody thinks, well, 30 watts, okay, I need to supply 3.5 amps. But as you're bringing voltage up on this power supply, it's going to require a lot more current than that, because it's going to look like very little ohms over here into here. So the ohms goes down when the voltage is low, which is kind of a tough thing for a power supply to handle. It has to, when the voltage is high, the current's lower. So there's a couple things you do with the switch mode power supply to allow it to work. Because if your load is applied, and let's say you start bringing it up and it was 1 volt, and let's just say the efficiency is 100%, which it's not, so you actually have to supply more power over here for your 30 watts here. So maybe it's 32 or 33 watts here, or even higher maybe. Well, if you're even 30 watts over here, you're going to say, wow, if I'm down at 1 volt, I have to supply 30 amps at my input. That's a lot of current. So what you do is there's a thing called under voltage lockout. You'll find this in data sheets, this under voltage lockout. It's under voltage lockout, right? Okay, so you'll find that term in data sheets. And what that means is, like, let's say in this case, this boost converter, maybe at 9 volts, it's going to drop out, because it's going to say, wow, I'm not designed to handle more than so many amps at my input. And you want to protect that transistor at the input, because you don't want it supplying those gigantic peak currents, because it's not, say, 3.5 amps or 30 amps. It's actually a lot more, because the switch is on and off. So when it's on, it's supplying all the current. When it's off, it's not supplying any. So the peak currents are much higher, actually. So under voltage lockout protects the power supply, or the boost converter, your DC-DC converter, at low line, so that it's not pulling too much current. Which also protects, because you'd have an EMI filter, you'd have other components, or even the pins of your connector are going to be limited by how much current they can handle. And all those parts you're going to want to have some D rating. If you have a part rated for 1 amp, you don't want to put 1 amp in it. You want to put maybe half an amp through it, depending on the D rating of it. So yeah, so this is an important function, and this negative resistance, concept, or function of the power supply creates this situation where you need things like that. There's another thing called soft start. And soft start, it's usually in the form of a capacitor on a pin of the chip, and that chip will have like a current source built into it, so many microamps or milliamps that's going to supply to that pin. You put a capacitor there, and that, because it's a fixed current, it's going to ramp up linearly, and that voltage on that pin is used to drop your current sense voltage, your threshold where your current sense is going to trigger, because you're going to be monitoring current, but that's going to be converted to a voltage. And let's say the chip looks for a 1 volt peak to current limit. Well, when that capacitor, your soft start capacitor, is at 0, it's going to be limited at a much lower voltage. And as that capacitor increases, it allows that to go up to the full 1 volt current sense trip point. So that soft start helps a power supply turn on, so that these low voltages, even after it's turned on, after the UV under voltage lockout allows it to turn on, you still have this range where you just want to be nice to the power supply, and you want to not stress everything when it turns on. One of the things that happens when a power supply turns on, it has input capacitors here, it has capacitors out here. So not only is it supplying this load, but it also is trying to fill up those reservoir capacitors. So everything looks like a short circuit when it first turns on. It's got to pump those guys up. And what could happen is you'll start to come up, the power supply will trip, overcurrent trip, it turns off, turns on again, then it comes back up a little bit higher, turns off, turns on. And these output caps can get charged up a little bit, and if that happens soon enough before the load drains the capacitors, you slowly, stair step the output up where it turns on. And that's not a great way for a power supply to start up. So you want to consider all that stuff designing a power supply. The undervoltage lockout, that's another thing. So let's say if it did turn on at 9 volts, when it starts drawing current through the EMI filter and inductors and all those components here, there's going to be some voltage drop on those parts. And when that happens, it could drop below 9 volts, the input. And if the undervoltage lockout was just a fixed point, then it would turn off because it's under 9 volts. But then when it turns off, there's no current running through those parts, so it bounces back up, turns on, turns off, turns on, turns off. You get caught up in that kind of situation. So what we do is the undervoltage lockout pin will have hysteresis built into it, which means, let's say it turns on at 9, then it doesn't turn off until the voltage drops to, say, 8.5 or maybe even 8. So there might be a half volt or a full volt. It's generally somewhere in that area. And that's usually enough to keep your voltage input. Now that's on a lower voltage power supply. If you're doing a higher voltage power supply, it's going to be maybe a 10 volt or 20 volt hysteresis. So it just depends on kind of voltage range you're in. But I don't know if it's 10% factor or what. I never really thought about it that way. But the point is your voltage is going to drop a little bit, and you don't want that thing to happen. Which that can also cause a staircase situation where you turn on, charge up the output a little bit, turn off, turn on, so you can, that can also get that staircase situation going on. All right, the other thing, maybe the last thing we'll talk about, is the power supply. When someone's going to test it, they're like, okay, it's limited to 9 volts. So 9 volts is going to draw a little bit more than 3.5 amps. All right, I'm going to give it, even a little bit more than that, 4.5 amps. So I'm going to limit my power supply over here to 4.5 amps because I don't want to damage anything. And I want to make sure the thing's running. So the guy gets the very first board off the line. He's being all careful. He's got this, current limit controlled. And he's bringing up the voltage, and he's gives you a call and says, hey, your thing's short circuited. It's not running. Well, remember, this boost converter is only turned on. That switch has got a duty cycle, right? So when it first turns on and these reservoir caps aren't all full yet to supply the current for each one of those cycles, then they have to fill up, plus they have to charge this guy up or get this guy running, and that, say, 4.5 amps isn't enough. It might actually need 10 amps to get going. One way to experiment is make sure your load's turned off, so all you're doing is charging up these caps and these caps, and then that'll help a lot. And when you first start turning on the power, if you don't see a lot of current right away, then probably there's nothing shorted inside your converter. Things are probably working okay. And anyway, so I guess I'm getting into some troubleshooting stuff, but so that's negative resistance. You can see how it can impact several levels of the design or test, and it's just something to be cognizant of and something to understand. So looks like my meters have fallen asleep on me. These two guys. The Flute 27, he seems to go strong. I don't know if I've seen him turn off on his own yet. Haven't looked up in the data book to see if there's a timer on it, but I'm not mad at that at all, because it's more frustrating to turn meters on constantly than to turn them off when you're done, right? Unless you forget. Alright guys, hey, give the old video a thumbs up. That helps the analytics a lot. And subscribe if you haven't done so. And thanks, patrons. Appreciate you. And somebody's going to get this on Father's Day. Well, I'll pick a winner on Father's Day. Again, if you're not a patron, it costs as little as $1 a month to become one, and I've got some other things I'll be giving away. But yeah, alright guys, I hope that was good. Give me comments and suggestions or remarks about this, and if you understood what that negative resistance is. I think I'm going to demonstrate this a little further, like this history sees on this power supply and things like that in the next video. Okay? Alright, we'll see you then.